Well, there's a couple of ways that we can do this. Now, I did it in red as though there was something wrong. All that I'm saying is it's a little trickier if I do it this way. Watch this. I've accounted for this root x. I've accounted for that root x because they're both u's. Now I have to account for the dx. So my dx is going to, if I just solve algebraically, is going to end up being 2 root x du, right? And you see what's going on here? So I get 2 root x du. I've got an x and a du, and that is just about as confusing as can possibly be. However, you may see, now again, when you're new to this, you want to keep it as parsimonious, as simple. Look at this. 3 steps and I'm done. Now I'm having to do all this. What's going on? I have to back substitute. I know that u equals root x. So now I know that dx is equal to 2u du. Now when I account for this, remember, I'm going to have the integral from 1 to 4. My new limits are going to be the same. But let's start out. I know that this is going to be e to the root x over root x dx, right? I know that this is going to turn into the integral from 1 to 2 because right here, remember, I changed my limits. And I'm going to get, okay, well, let's see, dx is 2u du. So I'm going to have a times 2u du, right? And then I'm going to have an e to the u and then over u. Now, notice my u's cancel, and I end up with, if I pull the constant out, 2 times the integral from 1 to 2 of e to the u du. I end up with the same thing, exactly the same thing. However, this one is harder to get to. It's more algebraically cumbersome. I've got a lot more steps to do, and it can get really confusing. So, in the end, just keep it simple. Trust me. And let's do another one. How about this guy? Let's do, how about the integral from e to e to the 4th of dx over x root ln x. I like that one. That's a good one. Great problem. All right, now here's another little tour guide tidbit. Look close. Look at these limits. These two guys right here, right? I mean, those are some suspicious looking limits. I know that I'm going to be changing my limits when I do a u substitution. Oh wait, I'm getting ahead of myself. Has anybody memorized this function and its antiderivative? Of course not, right? It's like, I don't freaking know, square root of ln x. And what? Not going to happen. Okay, so we know now we're in substitution mode. Okay, now I will warn you, it's going to get more complicated as we learn more and more techniques of integration. But for right now, you've really only got 2 skills. Either you memorized it or you got to use substitution. All right, so hopefully you see at this point, if I think about it, the derivative of the natural log of x is equal to 1 over x, right? True, and there's a dx over x. So let's go play. If I have u equals ln of x, then du is equal to 1 over x dx, which is exactly what I need. That's perfect. All right, let's redefine our new limits. U of e equals the natural log of e, which is 1, and then u of e to the 4th equals the natural log of e to the 4th, which is 4, which implies that my new integral is the integral from 1 to 4 of, now all I'm doing is back substituting, right? I'm going to account my dx over x is just du, and then my 1 over root ln x is just 1 over root u. And look at that. Now, look at this. Once I change my limits, it's as though this function never existed. These two are identical functions. They will give us the exact same values. Believe it or not, if I wanted to ignore the limits and just do this like an indefinite integral and then back substitute and put in my original limits, I could. But remember, the purpose of all of this substituting is to make it simpler. Now, I don't know how much experience you guys have had with 1 over square root of u, but it's going to be 2 root u. That's its antiderivative from 1 to 4. And this is equal to 2 times root 4 minus root 1. Root 4 is 2. Root 1 is 1. 2 minus 1 is 1. And there's my answer. Nothing to it. Okay? All right. So, fun stuff. These are a hoot. All right? Let's do one more. This one gets a little bit trickier, but it teaches a really good skill. Watch this. We're going to go the integral from 1 to 2 of x times the square root of x minus 1 dx. Now this one's actually a little bit tricky because if I let u equal root x minus 1, then I know the derivative, I mean think about this, if I take the derivative of root x minus 1, then I know that this thing is going to be 1 over 2 root x minus 1. Well, that doesn't help me. Okay, if I let if I take the derivative of x, I get 1. Well, hopefully you remember that I told you, when in doubt, when you're stuck, right? When you're absolutely stuck and you're in a corner and you just want to try something, let u equal the nastiest thing. Well, we know that this nasty thing is not going to work. However, what if I were to let u equal x minus 1, right? Then du would equal dx, right? Because the derivative of a linear term is just the slope. So I've got this accounted for and I've got this accounted for. How am I going to account for that? Oh, algebra. Can't I rewrite that as x equals u plus 1, right? Remember, it's just substitution. All that I'm doing is substituting one term for another. Now let's see if that even helped us out. First things first, let's change our limits. I know that u of 1 is 0. I know that u of 2 is 1, right? So that implies that this guy is equal to the integral from 0 to 1 of what? Now let's look. X is u plus 1, right? X minus 1 is u, so this term right here is going to be root u. So times root u, and then du. Okay, now does that help? Well, let's look. I don't know how to solve this, but I know that I have the distributive property, right? I could just distribute the root u through, and what do I get? I get the integral from 0 to 1 of u to the 3 halves, right? U to the 1 times u to the 1 half. And this is plus u to the 1 half, or the square root of u du. The antiderivative of u to the 3 halves is 2/5 u to the 5 halves plus 2/3 u to the 3 halves, right? I just added 1 and divided. That one's easy. And this is going to be from 0 to 1. Now this one's nice because the 0 just makes everything 0. So I'm going to get 2/5 times 1 to the 5 halves plus 2/3 times 1. I know you guys, I don't need to write this. And then, of course, minus 0, because when I stick 0 in for both, I get 0. This ends up being 2/5 plus 2/3, right? What is that? 6 plus 10 is 16/15. And that's my answer. Isn't that fun? Those are fun. They're like little puzzles, but it does take a whole bunch of work to get them done. Okay? It does take a whole lot of work to get them done, so got to be careful. And we're going to do so many of these, it's not even going to be fun. Okay, let me give you a couple of quick rules, and then we'll be done with the section, and we'll be done with the semester, which is really cool. All right, let's go even-odd rules. Even/odd rules. These are just kind of thrown into this section. I don't really know why your author chose to put them in here, but I want to make sure that you get them. All right, so part one, if f is even, which implies that f of negative x equals f of x. Okay, then this implies that the integral from negative a to a of f of x dx equals what? Well, think about what even really means. I mean, this is a useful algebraic use, but really think about what it means. An even function is symmetric with respect to what? It's symmetric with respect to the y-axis. So whatever's going on over here is also going on over here, right? I mean, think of things like cosine, think of things like x squared, et cetera, et cetera. So if you think about it, I know that it's even and I can figure out the area of this, then it's really easy to figure out the area of this. They have to be the same. I just double it. And sometimes it's useful to not have to deal with negative values because they frighten us, right? So we could just simply say that this is equal to 2 times the integral from 0 to a of f of x dx. Now look at this. 2. How about if f... Now notice, wait, I got to slow down. Your spidey sense should immediately start tingling when you have an integral from negative a to a. That's the rule. If you see an integral from negative anything to anything, start asking yourself, is the function even or odd? Okay, that's really key. So the first move, if f is odd, all right, then we know that f of negative x equals negative f of x, right? And then, what do you think is going to happen there? Well, what's a good, solid, odd function? What's your favorite? Well, some would say, ooh, x cubed. That's a good one. Some might say tangent. Tan looks a lot like x cubed. How about sine? Sine's an odd function, right? Etc. Etc. What do you notice? If I take the integral from negative a to a, what's going to happen? Well, whatever area is happening to the right of the y-axis is also happening to the left, but it's across the x-axis, right? Remember, that's called origin symmetry. This is y-axis sim, oops, and this is origin sim. Remember that? So what happens with these areas if this is area 1 and this is area 2? Well, remember, technically this is less than 0 and this is greater than 0, so they cancel out. So the integral from negative a to a of f of x dx equals 0. Isn't that nice? Now that's a freebie, but remember that these rules really only come into play if I have the integral from negative something to something else. Okay? Well, that's about it for 5.5, and that's about it for the semester, which is pretty exciting. So, excuse me, big yawn. Check it out. Like I say, we're going to be doing a boatload of these, so enjoy and just take your time. And just, like I said, this is the most important skill that you can pull out. Very much like taking chain rule, taking derivatives using chain rule was the most important thing that you could do with derivatives. Okay? So thanks for your time and attention, and have a really good day.